So we're going to be talking to you about going from data to meaning. So effectively what this means is taking data and doing something useful with it, making it mean something to your business, to your organization. It's a kind of a step-by-step guide. It's a walkthrough of the steps you would use to approach a data problem. And we use a specific example during the talk to illustrate this and to highlight this. So the first thing I'm going to do is realize I don't actually need this because we're presenting from there. The first thing I need to ask you is, how many of you have heard of Hadoop? Okay, so keep your hands up. How many of you have built your own personal Hadoop cluster? Okay, so not so many of you, right? Okay, so it sounds like fun though, doesn't it? So perhaps it's something we should try. Let's try building a Hadoop cluster. Can we switch to the demos? Switch to the machine. Right, brilliant. Okay, so as in the best Julia trials principles of demos, we have some things we've set up already. We have a compute engine virtual machine instance that we've set up to run this demo. But that's pretty much all we've done. Well, actually, we've also done some configuration as well. So I have this virtual machine here, which I'm going to SSH into. And to do that, I'm going to go to my shell. Everybody see that? Yeah, I think it should be good. And what I'm going to do is SSH into this machine, if I can find the appropriate command. So I'm using a command line tool from our Cloud SDK to SSH into that machine. And here we are. It's a real Linux box. We can do ps -ef to see what we've got running. And what we'll do is we'll cd to /user, -bd, oops. I'm not very good at typing either. So what I'm going to do is run a script. And we have some configuration we've already done beforehand on this. Oops, I really can't type. So we're going to run this command called bdutil, which I'll talk about more briefly. And for those of you who have not heard of Hadoop, we'll have a slide afterwards that will kind of just position that. For those of you who have, this could hopefully be impressive. One thing I want to do actually first, because I forgot to do it earlier, is change my configuration file. So, oops. See, the demo gods are still favoring me because I haven't broken anything yet. So, Hadoop is a distributed system for performing data processing. And for that, you need a number of workers. And I'm going to provide 20 workers. So I'm going to ask it to spin up 20 workers in my Hadoop cluster for me. So what I do is, I was testing on smaller clusters because I've been having problems with this particular demo. And I've been using a small size to make sure it works. And I've got to change it. So that's my fault. And .bdutil deploy, that gives us a list of our configuration options. This is the configuration that will be used to build our Hadoop cluster. We have num workers, 20. That's what we just changed. It's going to create a bunch of compute engine virtual machines to deploy Hadoop on. Some more information about our project, our image that we're going to use, the zone we're going to use, etc. And the prefix we're going to use for these virtual machines is NYC, just to prove it's real. And as you can see, we don't have any virtual machines currently, apart from the one that we're using to do the setup. So I say yes, and that goes off now, and it's effectively doing a lot of asynchronous tasks to create instances. We have lots of machines, workers, 20 of them that are going to come up, and we have one name node server, a master server, that will manage and coordinate the whole of the Hadoop cluster. So that's doing that in the background, and that's going to take a little while to finish. But we can see, probably, if we hit refresh. Now, the Cloud Console, the developer's console, doesn't refresh very often, so you often have to go into to it and do a refresh. And here we can see 4 instances coming up. There should be 20 of them. Okay, why is it doing that? Now I'm puzzled. Okay, so it should actually show them in various different states of provisioning, but it's actually showing them all provisioned. So we have 20 nodes there. I think it's 20. Can't see any missing. But normally you would see all of them, and you would see some of them were being provisioned, and some of them were up and ready. The green tick here tells me that that's up and running. We also have this NYC-NN, which is our name node, our master coordinator for the whole cluster. And, oh, that's a disk, that's why. Clicking on the wrong thing. So these are the instances being provisioned. So this one, NYCDN18, is still being provisioned. All of the others are already up and running. The disks that will be used by these virtual machines are also being created as well. I can go to the IP address of the name node, click on it, and I can simply enable HTTP traffic for that virtual machine. We're going to need this. This is our Hadoop master. This is how we're going to interface with the Hadoop cluster later on. So I click apply on that, and that will go off and do something in the background and effectively enable HTTP and HTTPS, opening those ports up on that instance. So because we don't have any minions in this talk, I thought we should have one. So that's just an aside, though. That's not really key to this talk. We do have minions in the talk later. I hope Julia has minions in her next talk as well. He's so cute. Right, so can we go back to the slides, please? Unfortunately, this kind of it requires going backwards and forwards to check. And because we're controlling the slides from there, I can't quickly switch backwards and forwards. So we'll come back to that deployment, Hadoop deployment soon, and see what it's doing. So for those of you who didn't know what Hadoop was, Hadoop is an open source implementation of MapReduce. MapReduce is effectively a mechanism by which we can do distributed computing. It was invented by Google. We published a white paper back in 2003. It consists of two main steps. The first is a map step. Effectively, this is performed on small subsets of the data that you want to process. And it's distributed across all of these nodes in a cluster. We created one with 20 in this case. And then all of the output from these map jobs are pushed into a reduce job, in which we can do other things as well. This is the next part of the phase of the MapReduce. In this case, we're going to reduce the data set down. The demo we're going to look at later only has a map step. And the reduce step could effectively be run across multiple nodes as well. MapReduces can be run on both structured and unstructured data. And Hadoop, to give it its full name, is Apache Hadoop, and has this nice little elephant. So Hadoop itself has a file system, a distributed file system, that allows it to support this notion of distributing subsets of the data across a huge number of nodes in a cluster. And we only have 20 nodes, but you can imagine a Hadoop cluster with 1,000 nodes. Somehow we have to distribute the data across all of those nodes. And the way Hadoop does that is through a file system called HDFS, which is its own file system. And Hadoop is completely open source, by the way. When we're running Hadoop on Google Cloud Platform, we have several managed data services at our disposal, including BigQuery, Data Store, and Google Cloud Storage. So what we want to really be able to do is store data in those data services, and let Hadoop access the data directly from them, rather than creating a HDFS file system on multiple nodes and then copying all of the data around. We want to do it in situ within the data service that we already have in place. So we have these connectors. We have a BigQuery connector, a Cloud Storage connector, and a Data Store connector. BDUtil is a very simple script. It's effectively a wrapper around the Cloud SDK. I think Jerome mentioned the Cloud SDK in his talk. And the Cloud SDK is a suite of tools that we use for managing everything within Google Cloud Platform. In this case, BDUtil will deploy the Hadoop cluster for us. It will create all of those instances and then configure them with the Hadoop software. It also installs and configures the GCS connector, Google Cloud Storage connector. It's also highly extensible as well. We can run individual commands on the nodes as they come up, or we can also run scripts as well. That's what BDUtil is. That's the util we used to actually launch the demo earlier. I'd like to go back to the demo now, if possible, just briefly. Okay, so it failed. And why has it failed? Sorry. Really, honestly. So the two times I ran it up there, it was fine, and it was failed in that one. Okay, I don't know why it's failed. Do I care? I'm going to spend a very short amount of time looking at the debug file, because I want to know why it failed. But we won't get hung up on this. We'll continue, because we can continue. In the face of adversity, we always continue. See, you find it funny. It's me, I'm falling apart on the stage. Okay, you're not telling me much here. A back-end error. Okay, well that's very useful. Okay. So it's a script that's highly reliable, but maybe needs a little bit more work. Okay, so can we go back to the slides, please? Okay, so if you were a room full of data, if this was a room full of data scientists, are you all data scientists? Anybody not a data scientist? I think there's quite a lot of you, right? Okay, so if this was a room full of data scientists, I'd be talking about big data, but let's not get hung up on that term, because some people find that kind of difficult to get their head around. Maybe, big data, that's not really for me. We're just going to be talking about data, so let's forget about that term. Apart from giving it a quick definition, big data is effectively a data set or a collection of data sets that are either too complicated or too large to be handled by what would be called traditional data processing techniques. And I guess today's data processing techniques in the future will be traditional ones as well. So, but what it's really become in reality is an approach to data analysis that just would not be possible with those older, more traditional data processing techniques. And I really like this. I really like this comic strip. Outside in the world, we have flying cars. We have, imagine what it takes to coordinate a bunch of flying cars. We have personalised offers being made to a guy called John Anderson. We have the management of traffic flow throughout a city centre, making sure that people could be guided to the appropriate parking spaces. All of these are big data problems being solved. And inside the office, there's an exec guy talking to his minions. So I did mention minions in this talk. So, okay, we haven't really got a bed on or anything that we can mention minions in each talk, but they seem to come up everywhere nowadays. The exec guy doesn't really get it. He's not ignorant or anything like that. He just hasn't hit him yet about how important this stuff is. And it really is important, and that's why we're having this talk today. I just really like this comic strip. So, some more examples of gaining insight into data. Personalised insights into your customer base is extremely important. And I imagine in North America, like in the UK, you have grocery stores, loyalty cards, and other stores as well. I guess all of the big stores have loyalty cards, which can track your activities and make you special offers at certain points. Things like in-app purchases, point-of-sale offers, another interesting one. You go into a bank to make some query on your account. The bank teller brings up your details, and the screen also tells them about things that might be interesting to you given your current financial circumstances, and he pitches them to you. User retention activities are also extremely important. For games particularly, things that have a pattern-based usage, where you could use the game for a certain period of time and then stop using it completely. And if we're monetizing on that game, on the usage of that game, we want people to use the game more. So we can actually analyze the way people interact with the game and make decisions based on somebody's interaction and to when to make them free offers. Those kind of things. Things that might make them or continue to engage them in the game for longer than they would have done normally. Predicting health problems. We've done this before at Google with identifying patterns of searches for flu, predicting flu epidemics. Optimization of websites through analytics is extremely important these days. That's a big data problem, and it's solved by things like Google Analytics. Then there's things like enabling future breakthroughs in biology and medicine, which we'll come back to. And finally, my favorite one, which is autonomous traffic lights and flying cars. So I want traffic lights to make decisions themselves rather than being red. And no cars, no traffic. I want them to say, there's no traffic, I can turn to green and let me go. That's a problem I'm really determined to solve in my lifetime. So if anybody wants a job. So, now that we've looked at the big picture, let's talk about a specific application of the Google Cloud Platform to a data problem. So for this, we're going to need to walk through a specific example, and we saw a few of them on the previous slide. There are many. There are probably an infinite number of data problems we could look at. So we had to choose one specifically, and we have chosen one that's specifically about genomics. And the Google genomics team, who were formed, I think, in April, They're busy making tools that will be used by life scientists to really handle the incoming flood of genomic data. And genomic data is huge on its own, but we also have a huge population. So we'll have a huge data set to mine to find information out from. This ultimately will enable future breakthroughs in biology and medicine. So scientists working with this data know what they want to do with it. They just want it to be easy. And this probably resonates a little bit with you, where you probably have some good idea about what you would like to do with your data that your organization generates. But you just need the tools that would make that very easy to do and very fast to do. So at the intersection of data science and life science, there are discoveries and breakthroughs to be made. And in that particular area of science, maybe things that could change the game for us all as a race. But you're probably not in the genomics business, and now I've set this up already. Is there anybody in the audience who's in the genomics business? So we've already spoken. So I knew. I was going to ask this question. I didn't expect anyone to put their hands up, but we have somebody who's in the genomics business, which is fantastic. But however, if you're not a data scientist, your particular business, no doubt, is also a complex affair, and it requires specialized knowledge, and you're probably an expert in your own domain. So no doubt there are insights to be gained at the intersection of your business with data science. So the first question we need to ask is, where is your data? And most companies have a lot of data lying around, usually in one or usually more operational databases. The examples I'm going to be showing you are from the Personal Genome Project. I'm not sure if there's anything you guys are familiar with, but this is what we're going to be looking at, the Personal Genome Project. So the PGP is effectively creating a freely available resource, a scientific resource, that brings together 3 types of data: genomic data, environmental, and human trait data. So that's information about the genetic makeup of a person, the environment in which they were brought up in which they live in which they work in from day to day, and also traits that they exhibit. Do they have diabetes? Did their mother have a brain tumor? Are they susceptible to broken limbs? Do they have green hair? Or do they have yellow skin and look something like him? Oh, you can't see him. I'm showing a picture of a minion, but you can't see him. So let's just go back to that slide. Hello, go back. So this is the data set we're going to be working with, and we have some genomic data stored in Google Cloud Storage, which we're going to be using. So no matter where your data is now, there are usually 2 things that are true about it. The first is it's not in a place where it's best or most easy to analyze. And it's also probably not in the right format. So this brings us to extract, transform, and load, which is the process of taking data in one place in one format and moving it to another place in a different format. Now, this might be fairly straightforward and fairly simple to do on a small amount of data, but what if you have a lot of data? What happens if you have a huge amount of data, so much that will overwhelm the tools that you have available to you today? So that's what we're going to be talking about, and that's what this dumper truck represents here. So let's talk about our data in more detail. I'm not going to go to the demo yet, but so we have all of this data stored in Google Cloud Storage. We have a tool here we're using called GSUtil to actually list that data. We can actually effectively interact with this data stored in cloud storage as if it's local just by using this tool GSUtil ls. And we can see we have a couple of files listed there, only 2 of them. There are 175 files in the data set in total, representing 174 participants of the PGP and 1 duplicate for some reason. Each file is about 17 each file is about 2.3 gigabytes in size and has 17 million rows. They are identified exclusively in the file name with an identifier. In this case, we have HU011C57 and HU016B28. These are individual participants in the Genome Project. The one problem with that is that data, that participant ID, is not in the data in the file. So we have 17 million rows of data, and none of it contains information about who that participant is. So that's the problem we want to solve with our demo. So can we switch back to the demo? So this is the list of all the files, the 175 of them that we have. And I'm just going to quickly run a script. So I have to kind of juggle between going back to the slides and going back from the demo. So I'm just going to run this script on this file now. And I'm going to pipe that to more. And this is taking that file that we had before, and it's prepended, added a column to the data set, which represents the ID of the participant ID, the ID of the participant in the genome project. And this is what we want to output. What we could do at this point is we could actually pipe that out to a file, redirect that out to a file. But we have 175 files, and there's 17 million rows of data in that data set. It could take a long time to process one file. Well, how are we going to process 175 of them? So can you go back to the slides, please? Right, so we can run that script on one file, but what happens if we want to run it across all 175 of them? So this is where MapReduce comes in. In this case, we can run a command on the thing that we identified as a name node earlier, the master machine, and we can, if our cluster was up and running, unfortunately our cluster isn't up and running, so I can't interact with it, we would run the command, Hadoop command, and pass in some parameters. One would be where the input data was, and that's the third line in this command string, the lower command string, minus input. Then we would specify the mapper script. This is the script that would be used for the map step. Then we would also specify the number of reduce tasks. In this case, there's none. We're not doing any kind of reducing. Our map script is very simple. We need to remove the duplicate data and add that column right at the start of each row. And then we need to say where we want to output it. And we're going to output it to Google Cloud Storage in a bucket called bigdata-roadshow/output. So if I were running the demo now, and I can't because the cluster didn't deploy correctly, I would submit that job, and we would see in the console we had 20 nodes available to us to actually run the job. And then we would drill into the job and look at the specific details of the job, and we would wait for it to complete. And this job takes about 5 minutes, 41 seconds. I would have actually worked on a 17 file set, about a tenth of the original data set, which would take considerably less time to run. And we can see that the map job, there were 704 of them, and they've completed successfully. There was nothing to do in the reduce step, no jobs at all. And that was successful. So that's now processed our data. It's moved the data from one place in one format to another place in another format. Exactly what extract, transform, and load specifies. So that's good. So some more information. 435 gigabytes roughly of data was processed by that Hadoop job, and it takes about 5.5 minutes. And 3 million rows of data. So then we could delete the cluster. I really like to delete the cluster because it failed me, didn't it, Totoro? Didn't it? Hey. One thing that never fails me is BigQuery, though. So we're going to talk about BigQuery. So there is more. There's always more. At this point, though, that may be all you need to do on your data, and you may be doing that on a daily basis. You may be processing your data from one format in one place to another format in a different place. We do that at Google all the time, contrary to popular opinion. Some people may actually get that joke, but others might not. We still do lots of MapReduces, and MapReduces can be a key part of an organization's data processing toolkit. But there is more. In this stage, we want to actually process the data and get insight from the data. So we're going to use Google BigQuery. And I think Jerome mentioned BigQuery already. BigQuery effectively allows us to run interactive queries across massive data sets. And we're talking about terabytes of data, billions and billions of rows of data. Interactive queries are great because you can ask questions of the data and then you can modify the question you asked based on the results that you've just seen. We do this all the time with our log files. So we have lots of log data internally at Google. We have the internal version of BigQuery, which is called Dremel, and we run interactive queries across the log files that we have to see what's going on. There's no limit on the amount of data that you can store and process in BigQuery. It's very easy to use. You don't have to administer anything. You don't have to create a machine. You don't have to do the build process here that failed for us. You have the machines available to you that are needed to process the data. We provide those dynamically, automatically. It has all of the convenience of SQL, as we'll see shortly. It's an API. BigQuery is an API. We'll see a console shortly, but that was just written on top of the API. The first 1 terabyte of data that you process per month is free. It provides a very familiar database structure. So you have databases, you have tables within the database. Data management is very easy, and it has the opportunity to import data atomically very, very quickly. There are various methodologies you can use to get data into BigQuery. So can we drop back to the demo, please? So this is the BigQuery console. Can everybody read that okay? Anybody not read it? Okay, cool, excellent. Okay, so we have plenty of public datasets that are available and sample datasets as well. So BigQuery samples are datasets we can play around with. We have one called, I can't see it completely there, Wikimedia page views. And this is a Wikimedia pages that were viewed on a given date. And it's all sharded into several tables. Here we see them by date and go all the way down to 2012-07. We haven't got any later data than that, but we go up to 2012-07. So we have sharded data by month, effectively, for these page views in Wikimedia. And what I can do is I can load up a query, and I can zoom in on my query, make it a bit bigger, and I can run this query. So basically, this is BigQuery. It looks very much like SQL, if anybody's used SQL already. We're going to be selecting the title and the number of views, or we're going to sum the number of views for a particular page. We're going to do it across a number of those tables, so we can actually do this across multiple tables, one query across multiple tables. We're going to add some where clauses. The important ones are language equals EN and the regex expression here. Something beginning with G, has an O in it, and ends in E. Can anybody think of a word that might fit that? Not sure. Group by title and views, order by views descending. There's a little bug in this. I don't know how I ended up with that, but it still works, so I'm not going to worry about it too much. Come back to here. I can click on this green arrow down here and see how much data that will process. And that's going to process 507 gigabytes when it's run. It also tells me that the query I'm running is valid. So we get 1 terabyte of data free per month. This is going to use half my quota up in a month. And obviously, I've run it a couple of times already just to practice to make sure it was working. So I'm already over the top in terms of using my quota. But don't do this unless you want to spend money, because it's a big data set. So let's come back to here, and we're going to run that query. We'll go down here where it says query running. And it takes probably about 12, 13 seconds. If there's any problems with the timing, it's because of it's trying to contact the job that's running remotely. And that could be impacted by the Wi-Fi speeds and various other things. So we processed that, 507 gigabytes processed in 18.4 seconds, and we can see sometimes it's hard to play with the real estate. Google. Of course, I didn't think about that. And back in those days, Gautier were famous. Again, that's another joke that many of you might get. Google Chrome is also quite popular. And again, sometimes when I'm running this demo, I do it in different languages. So by running it in France, I'll do it with FR as a language, and we see other interesting things. And you always have to run it beforehand to make sure nothing rude comes up. Well, you do. Can we go back to the slides, please? OK, so we need to load up our data. So imagine the data we created from our MapReduce job. We can load that up here. We'll enter the path to our cloud storage bucket. We'll say it's a CSV separated file, and we'll click Next, specify the schema for the data, and then we could import that data into BigQuery. Fortunately for us, that's already been done for us because we have, if I just close this down a little bit and go to display project. Big Gene. And you can do this yourself as well. So you can go to BigQuery, you can add this data set yourself to your own BigQuery setup. So we have, I'll just zoom in a little bit on that. We have 3 tables in our PGP database: CGI variants, phenotypes, and variants. And we care about this one, CGI variants. So we can select that, and then we can look at information about the schema. And, oops, bear with me a second. It's hard to know what I'm scrolling here. And this has lots of information that's genomic related. But remember, all this stuff can apply equally to your own data. This is just happens to be a genomic data. So back to the slides, please. I'm going to run out of time very quickly. So we can actually run a query to work out how many rows are in that data set. I'm not going to do that now because we're short on time. But we have, from the row count down there, about 3 million rows. And then we had to ask, what question do we want to solve? What problem do we want to ask of this data set that we have? So apparently, there's been some press about a study that effectively identified that a variant, a genetic variant, may have something to do with intelligence. And that, according to this headline anyway, is actually related to longevity. In fact, they've given it to mice, and it's made the mice live longer, and it's also made them smarter. I'm not quite sure how they measure that. I guess they have these little mazes that they run around. But I guess you can tell how smart a mouse is. It sounds like a pretty good deal, right? So let's find out how many participants of the Human Genome Project, Personal Genome Project, have this variant. We can also enter this variant name by name. It's called, I had to find it here, it's called RS953631. But variants are a little bit like asteroids. There's so many of them that they don't even bother to name most of them. Until one of them's interesting, then they give it some scientific name, like RS956314, which is great. If you search for RS95, I have to keep reading it, RS9536314, you'll get this page, which tells you it's in chromosome number 13, which is down there at the bottom. So we want to search chromosome 13 for that variant. We're going to do this in BigQuery. What we're going to find out is that we have these 2 columns, and one of them is sized badly because of the projector. LL1 sequence, LL2 sequence. If they are both empty, then they don't have the variant. If one is G and one is T, there's a variant in one allele. If they are G and G, they have both alleles have the variant. If they're question marks, it means we're not sure. We don't have that information within the data. So let's run that in BigQuery. Can you go back to the demo? So here's my query. We're going to be selecting things like the sample ID. This is the participant ID, the chromosome, the 2 alleles that we're really interested in. We're also going to be looking for a specific place because the list that we looked at earlier actually identified it was in a specific place within the chromosome. And we're going to be searching this CGI variants table. Does that make sense? Okay, so we're going to be looking in chromosome 13, that specific location for those variants. So I come back out, run the query. And that doesn't take very long to run, I think. Oh, it's run already. So 5.7 seconds elapsed, 117 gigabytes processed. Now you'll notice that that's less than the total size of the data. But that's because we're not looking at the entire data set. So BigQuery uses a columnar format for storing data instead of rows. So when it reads data, it only loads in the columns that you're actually interested in. So that's only a small part of the data set, as in this case. So we're only looking at a small section of the data. But we're looking at every row. So in terms of results, we have, again, BigQuery getting in the way with its. We have lots of options. We have 174 rows processed here. We can see one immediately that's actually got that chromosome in one allele, which is great. Okay, that's told us that we do have patterns. We do have participants that do have that genetic variant. We wanted to find out how many of them had. So let's modify our query. And this time I'll go back to my queue history rather than typing it in, because you've already seen my typing's lousy. And we'll run an aggregate query across that same data set. And I'll zoom in. In this case, we're looking for pretty much the same data, but we're counting the number of sample IDs that match. We're looking in the same place, and we're going to group by and order by it. So we can do aggregate queries with BigQuery as well. So I'm going to run that query. And come down here, query running. .5 seconds elapsed, 117 gigabytes processed. Resize this, and we can see, so 135 participants don't have that variant. 32 of them have it in one of their LLs, and 5 of them have it in both. Lucky people. They're smart, and they're going to live long. Yeah, I want some of that. So when they do genetic therapy, I want this one. So can you go back to the slides, please? So these are the results. We saw this already. They're just there in case anything falls apart. So basically what we've done here is effectively we've gone from data to meaning. We've had to decide what kind of questions we want to ask, because we want to have the data in the best possible format to answer them. We don't always know what questions we want to ask, but we always have a good idea of what kind of question we want to ask. Then we're going to say, where's our data? Is it in the right place? Is it in the right format? In this example, we've taken data stored in cloud storage. We've done an extract, transform, and load, and we've stored it into BigQuery. Once into BigQuery, we've actually run queries over it to gain insight into that data. Now, we could do this interactively. We could do this as much as we like. We could also program the whole thing and do it automatically. The last couple of things coming soon, we have Cloud Data Flow, Cloud Pub Sub. These are really important changes in the way we do data. We have Google I/O talks that will introduce you to them. I can't do them justice here, so talking about them would be pointless. We also have the ability to build Apache Spark clusters using the BD util. And Spark is an in-memory, effectively, cluster. Does much, much faster than anything we've seen today in terms of Hadoop, not in terms of BigQuery. And resources as well. I'll leave that slide up while I bow out. But these are the resources you can use to access to give you more information about what we talked about today. So that's pretty much it. We can talk about this later if you have any more questions, but thank you very much.